Hi, my name is Eric Wood, and I'm a research engineer at the National Renewable Energy Lab in Golden, Colorado. I'm here today to talk about enhanced load modeling and forecasting for transportation electrification loads, including electric vehicles. And I'll be describing one of the tools that we've developed at NREL for this kind of modeling called EVI Pro, the Electric Vehicle Infrastructure Projection Tool. Here at NREL, we don't manufacture vehicles or sell electricity or develop charging stations. And so as a national lab, our role, we feel, is to provide guidance to national, local stakeholders that are making investments in charging infrastructure for electric vehicles to help reduce range anxiety as a barrier to sales and also to ensure effective use of public and private investments. We've conducted a number of studies in recent years across the US primarily, focus on trying to address some basic questions related to charging infrastructure for electric vehicles, including how many stations are necessary, what kinds of stations are needed, and where those stations should be located. In order to forecast demand for electric vehicle charging, we typically think about charging infrastructure in two dimensions. The first is a spatial dimension, where we think about charging infrastructure necessary for charging vehicles within the communities where people live versus along the highway corridors that connect communities to enable long distance travel at a national and at a state level within the US. The other dimension that we think about charging infrastructure for electric vehicles is coverage versus demand. So early in a developing market, we would assume that a minimum level of infrastructure coverage is necessary in order to enable people to move about freely or have the potential to move about freely using an electric vehicle. This problem is typically a geographic problem that requires sufficient coverage within urbanized areas, as well as a minimum level of station spacing along highway corridors and able to connect stations. The other dimension that we think about is overall demand for charging infrastructure. And this is related to the number of vehicles and the frequency of charging that those vehicles would require. So we visualize these coverage and demand dimensions in the upper right corner of this slide, where early on in a vehicle's market share, we would assume that there is a gap between the amount of demand for charging that a region would exhibit versus the amount of coverage that they would need for the early adopters and able to move around freely within a given region. And so this is where we see a utilization gap between the amount of infrastructure that's necessary to get the market started versus how much demand there actually is for that infrastructure. As the market matures and we move from left to right on the horizontal of this plot, we see that the overall demand for charging increases as the number of vehicles on the road also increases. And eventually that demand for charging exceeds that minimum level of coverage infrastructure that's necessary. And we start to see a pull or a market pull where new infrastructure could be developed based on congestion at existing stations or an observed level of demand for new infrastructure. So in order to model the demand dimension of charging infrastructure and electrical load within urbanized areas, here at NREL we've developed a model called EVI Pro to attempt and conduct these simulations. EVI Pro is a bottoms-up model of charging behavior and charging infrastructure for electric vehicles that is essentially a two-step model. So in the first step of the model, we conduct individual driving and charging simulations, which I'll show on the next slide. And from those simulations, we're able to paint a picture of demand for infrastructure. And then in the second step of the model, we design a supply of infrastructure necessary in order to meet the simulated demand. So this process relies on high fidelity travel data from the region of interest and simulates those travels as happening in an electric vehicle, be it a plug-in hybrid electric vehicle or a battery electric vehicle. And then within the simulations, we try to resolve the amount of charging infrastructure that would be needed on an individual basis in order to complete the travel day that is present in the simulation. Given that EVI Pro relies on real-world travel data to run the model, we need to be well connected to different travel resources in the region of interest. This slide shows an example travel data set that we worked with from the Central Ohio region in the United States. This is Columbus, Ohio. And so in this case, we were actually able to work with a private company in the US to obtain a large data set of travel from this region. This data set included about 33 million trips over a 12-month period from the Columbus, Ohio region. And it captured a representative cross-sample of all of the different kinds of driving that vehicles in the area currently do. And this is the kind of information that we use for trying to forecast the driving that future electric vehicles may do in the region. There's also many other sources of data depending on the region of interest, including publicly available data sets, as well as transportation demand models that can be used for this type of a resource. So the previous slide showed a representative cross-section of travel data from a region. That is kind of a big picture look at all of the driving that happens in an area. Now that data is made up of lots of little pieces of information. And here we highlight kind of the fundamental building block that EVI Pro uses for modeling electrical load for charging. So here we show a representative travel day that includes 7 trips that are shown in the table in the upper right. For each of those trips, we've encoded a destination, be it the individual's home location, their workplace, or some additional non-residential location. And then we've also encoded the driving distance as well as the dwell time for how long the vehicle is parked at that location after arriving. And so having this travel data, we're then able to simulate depletion of the battery in the electric vehicle, in this case assuming a 100-mile battery electric vehicle over the course of a 24-hour period. And then we're able to resolve using EVI Pro the different options that the individual may have for charging and try to select an option that not only meets all of the driving needs for the individual, but also maintains the battery state of charge above some minimum state of charge level, while also trying to minimize the cost of electricity for the individual. And so this approach generally leads to a lot of charging at residential or home locations in most of our studies, using workplace and public charging in order to fill the gaps. And so in this example, you can see that over the 24-hour period, the individual had a level 2 charge at a workplace location. This is a charger rated at about a 6 to 7 kilowatt level. A direct current fast charge at a 150 kW level, and then an overnight charge at the individual's home location using a 1.4 kilowatt charger. So the process shown on the previous slide is repeated for a large number of locations and driving profiles in the region. Here again, we revisit our example from Columbus, Ohio. So having conducted thousands of these individual driving and charging simulations, we're then able to aggregate that demand in time and space and identify what we call hotspots for charging infrastructure across the region. So those hotspots are shown on this slide using these pink bubbles to show the parts of the city where we simulated the greatest degree of charging demand. You can see that many of those hotspots coincide with existing infrastructure, shown in the green dots, as well as some of the candidate locations that the city of Columbus was considering as of a couple of years ago for installation of new infrastructure. And so this approach allows us not only to kind of validate existing sites that are being developed for charging infrastructure, but also to identify new sites that local officials may not have identified yet as being good candidate locations. In addition to analysis within urbanized areas, we can also look at analyzing potential networks across larger geographies. Here we show an example from the state of Colorado, where we were evaluating a hypothetical fast charging network across the state's interstate and highway system. Using simulation, we're then able to examine the level of demand that we would anticipate being placed on the hypothetical network based off of the travel data from the region. In this case, we were using a publicly available travel survey from the state of Colorado. And as you can see, the majority of the demand that we simulated in this case was occurring along the north to south interstate running through the middle of the state here. And that is a really important finding for us because it allows us to anticipate what level of utilization might be reasonable to expect at each of these stations, where some are potentially very sustainable financially, whereas others may not be visited as regular, however would still be necessary in order to complete the network and enable someone to consider purchasing an electric vehicle in this region and having the ability to make long distance trips. In addition to forecasting demand spatially across a region, we can also use our modeling tools to look at the demand in time. And so here we're showing two example load profiles from a study that we conducted in the US state of Maryland. So here we were looking at a scenario that included 300,000 vehicles, plug-in vehicles operating within Maryland. And you can see the stacked area plot here representing the simulated load profile from two different scenarios. On the top, we simulate a scenario where vehicles are allowed to charge in an unconstrained manner. You can see the dark blue and the light blue sections at 16 hours in the day and 20 hours in the day, representing charging that's happening at home locations when people arrive back to their residence at the end of the day. These are from level 1 and level 2 home chargers, where the level 2 home charger is a higher power charger. We also simulate charging happening away from home in the gray and the red sections of the plot. This is charging happening at workplaces and at public locations, including level 2 charging as well as DC fast charging. And then on the bottom part of the plot, we show an example of what the load profile could look like in a situation where individuals are incentivized to charge late at night. So here we are assuming that there's a time of use rate in effect between the hours of 4 p.m. and 10 p.m., where the price to charge your vehicle is increased during that time. And we simulate people that arrive at home during those hours as delaying their charging until that price comes down at 10 o'clock. And then what we actually see is a big rebound that happens at that point where all of the vehicles come online to charge when the price drops. So it's an effective mechanism in this study for shifting load to later in the day, but does have the potentially unintended consequence of inducing this rebound peak. And my final slide shows two additional examples of time-resolved charging load profiles from electric vehicles. As with all of the material in this presentation, these are from light-duty electric vehicles used for passenger travel. So this is an example from the Denver, Colorado region where NREL is located. And here we're showing two scenarios where we're illustrating kind of the way that charging infrastructure is potentially intertwined with the shape of the electrical load profile from EV charging. So on the top, we're showing a scenario that we call a business as usual scenario. This is one in which the majority of vehicles prefer to charge at their home location and do so mostly using a higher power level 2 charger at a 6 to 7 kW level per vehicle. We also, in the top business as usual scenario, show a small amount of charging happening away from home at workplace and public locations. However, in the bottom plot, we show a different scenario where we try to simulate a world in which workplace charging is made available for free across the Denver metro. And in this scenario, we provide enough infrastructure within the simulation to accommodate all of the individuals that would potentially want to charge their vehicles for free at their workplace. And you can see that all of this additional infrastructure and the incentives that are given to drivers in the region really change the shape of the load profile. So shifting a lot of the charging load away from the evening hours at residential locations into the AM hours when people are arriving at work and trying to charge their vehicles at that location. So really just trying to highlight here the manner in which charging infrastructure and electrical load can be intertwined. So to summarize takeaways from today's presentation, forecasting demand for electric vehicle charging is a complicated analytical problem requiring an understanding of vehicle and charging technology, human behavior, and travel patterns. NREL's EVI Pro model provides a framework for modeling charging demand that accounts for these complex interactions. There are a handful of similar tools available, both within industry and within academia, for doing similar types of analysis, including the EV Toolbox at UC Davis, the BEAM model developed by Lawrence Berkeley National Laboratory, an intercity fast charging model developed by Oak Ridge National Laboratory, and a GIS-based planning tool developed by MJ Bradley. If you're an organization that's just getting started trying to forecast demand for electric vehicle charging, I would encourage folks to try to find local data on vehicle registrations to understand how many electric vehicles may already be in your area, and also to understand the size of the light duty and the medium and heavy duty fleets in your area, to understand what the potential for new electric vehicles in the region might look like. Thank you. So I'd like to thank everyone for listening in to today's presentation. I'd be happy to answer any follow-up questions. You could contact me by reaching out either to either of the two contacts listed here, here at NREL, and be happy to connect and talk more about load modeling for electric vehicles in other parts of the world. Thank you.